Good evening to all. Let's discuss about the gas turbine thermodynamic cycle. So in gas turbine, two types of thermodynamic cycle are used, and these cycles are called Brayton cycle. The Brayton cycle can be open type and closed type. So let's discuss each type of cycle separately. In case of closed Brayton cycle, you can see in the process 1 and 2 is the isentropic compression process, whereas suitable gas is compressed in the process 1 and 2, that is isentropic. 2 and 3 is a heat exchanger or heat addition, constant pressure addition process where heat is added by another fluid. And process 3 and 4 is expansion process, isentropic expansion process in the turbine. And process 4 and 1 is a rejection process, which is again constant pressure process. On PV diagram, you can see again process 1 and 2 is a compression process, isentropic compression process. 2 and 3 is a heat addition process at constant pressure. 3 and 4 is a isentropic expansion process, and 4 and 1 is a constant pressure heat rejection or removal process. Open Brayton cycle, where you can see the process 1 and 2 is a compression process, constant pressure process, isentropic compression process, where air is compressed in the compressor. Process 2 and 3 is a constant pressure heat addition, where the high pressure gas mixes and burnt in combustion chamber. Energy of the gas increases. Process 3 and 4 is a expansion process, isentropic expansion process in the turbine, and work is produced, power is produced. And 4 is again exhausted to atmosphere. That is how it is called constant process. That is why it is shown in dotted line 4 and 1. In fact, in case of industrial application, it is sent to the boiler for heat recovery and finally goes out to the stake or chimney. In case of jet engine, it is directly thrusted to the atmosphere. So process 1 into compression, process 2 and 3 is heat addition in combustion chamber, 3 and 4 expansion, isentropic expansion in the turbine, and 4 1 shown as dotted to consider as a closed system. However, at 4 it is exhausted to the atmosphere. That is why it is called open Brayton cycle. Now gas turbine, for the ideal cycle is shown on PV diagram. 1 and 2 compression process, 2 and 3 heat addition, constant pressure, 3 and 4 isentropic expansion process in the turbine. 4 and 1 is a constant pressure heat rejection. On TS diagram, temperature entropy diagram, it is ideal case. 1 and 2 is a isentropic compression process, 2 and 3 is a heat addition process, 3 and 4 is a isentropic expansion process, 4 and 1 is a constant pressure heat rejection process. Pressure P1 and P2 are two constant pressure process. P1 is a lower pressure, P2 is a higher pressure. Now the ideal condition in ideal gas, that is gas turbine cycle for ideal condition. Losses are neglected. Cp and K are considered and consider same for all everywhere and constant. So in compressor work head HC, what is this? Enthalpy rise in the process 1 and 2, which is equal to the work done by the compressor per unit mass, is a head. That means compressor work done per unit mass is equal to work head or head of compressor. For ideal case, we are now considering, we can write both are same. HC is equal to Cp T2 minus T1. T2 minus T1. Now turbine work head HT, work done by the gas per unit mass of turbine is equal to isentropic enthalpy drop in the process 3 and 4, because losses is not considered. So HT is equal to Cp into T3 minus T4. Heat addition process 2 and 3, is the process 3 and pro heat addition is expressed as H is equal to Cp T3 minus T2, T3 minus T2. Now we need to find out the overall efficiency of gas turbine system, that is denoted as EO. So overall efficiency is defined as the ratio of net work and heat addition. So net work will be Hn is equal to St minus Sc. Hn is equal to Cp T3 minus T4 minus Cp T2 minus T1. So Hn is written as Cp T3 minus T2 is bring here and T4 shifted here minus T4 minus T1. Heat addition H is equal to Cp T3 minus T4. So on overall efficiency is equal to Hn upon Ha. So EU is equal to Cp T3 minus T2 minus T4 minus T1 upon Cp T3 minus T2. This will cancel out. So we can write overall efficiency is equal to 1 minus T4 minus T1 upon T3 minus T2. In further simplification, we can write pressure ratio PR is equal to P2 by P1. So T2 by T1 is equal to P2 by P1 to the power K minus 1 upon K. If P2 PR is a PR, P2 by P1 is PR, so we can write PR to the power K minus 1 upon K. Similarly, T3 minus T4, this process, we can write same equation P2 by P1 to the power K minus 1 upon K. So PR to the power K minus 1 upon both are same. So we can write T2 by T1 is equal to T3 by T4. On further shifting, T2 by T3 is down and T1 goes up. So T1 by T4. And after 1 minus, so 1 minus T2 by 3 is equal to 1 minus T1 by T4. So on simplification, we can write T3 minus T2 upon T3 is equal to T4 minus T1 upon T4. So again, we can write T3 minus T2 upon T4 minus T1 is here and T3 goes up. So T3 by T4, but T3 by T4 is PR to the power K minus 1 upon K. So we can write T4 minus T1 upon T3 by T2 is equal to 1 upon PR to the power K minus 1. So we can write overall efficiency U is equal to 1 minus 1 upon PR to the power K minus 1 upon K. K is equal to a specific heat capacity ratio. It is Cp by Cv. So we have drawn the graph on pressure ratio on x-axis and overall efficiency on y-axis. Using this equation, you can with a different value of K. So when K is 1.35, this is graph for this. K is 1.4, you can see graph for this. So on the same pressure ratio, when K is a more, a specific heat capacity is a more, overall efficiency is also more. Now gas turbine cycle for actual condition are analyzed in two ways. When ideal gas when gas is considered idle or when gas is considered real. So in these two scenarios, we will see the efficiency of compressor, efficiency of turbine and efficiency of overall gas turbine cycle for case when ideal gas or second when gas is real. Now we'll consider the case number 1, that is for ideal gas consideration. Now you can see in TS diagram we have considered actual conditions, so there will be efficiency. 1 and 2s is the isentropic compression and 1 and 2 is actual. Similarly 3 and 4 dash is isentropic enthalpy drop and 3 and 4 is the actual enthalpy drop for turbine and this is for compressor. Since compressor is open system, so work done by that compressor on the system per unit mass, which is also called work head, is expressed in the process 1 and 2s. We can write HSC, C stands for compressor. HSC is equal to R into Kc upon Kc minus 1 into T1 into 1 minus P2 by P1 to the power Kc minus 1 upon Kc, where Kc stands for a specific heat capacity Cp by Cv for compressor. Similarly for turbine it will become Kt. But this expression will give negative value, so to convert into positive value we can write for positive HSC is equal to R into Kc upon Kc minus 1 into T1 into P2 by P1 to the power Kc minus 1 upon Kc minus 1. For ideal gas, we can write Cpc minus Cvc is equal to R, where Cp C upon CVC is equal to Kc. Kc is C suffix stands for compressor. So similarly, you can write 1 minus 1 upon Kc is equal to R upon Cpc. So Cpc is equal to R into Kc upon 1 minus Kc minus 1. So we can replace this. We can write HSC is equal to Cpc in T1 into P2 by P1 to the power Kc minus 1 upon Kc minus 1. So this is expression for compressor work head. Now the process actual enthalpy rise in process 1 and 2, we can write HAC, C suffix stands for compressor, CPC into T2 minus T1. So compressor isentropic efficiency is defined as CPC T1 into P2 by P1 to the power Kc minus 1 upon K minus 1 divided by CPC into T2 minus T1. So further CPC cancel out. We can write ESC is equal to C stands for again for compressor. So isentropic efficiency T1 into P2 by P1 to the power Kc minus 1 upon Kc minus 1 divided by T2 minus T1. But T2s upon T1 is equal to P2 by P1 to the power Kc minus 1 upon Kc. So we can replace this. We can write ESC is equal to 1 T1 into T2s upon T1 minus 1 upon T2 minus T1. So further we can write ESC is equal to T2s minus T1 upon T2 minus T1. So this is one expression for efficiency of isentropic efficiency of compressor. You can also use this expression. So for temperature form, this is expression. For the turbine now, ideal gas consideration, turbine is again open cycle. So work done by the on the turbine by the gas or system per unit mass is again work head, which is expressed in the process 34 dash sorry 34s. So we can write work head HST, T stands for turbine, R into KT upon KT minus 1 into T1, sorry, T3 into 1 minus P2 by P1 to the power KT minus 1 upon KT. But in ideal condition, work head is equal to isentropic enthalpy drop in turbine. So isentropic enthalpy drop is written as same thing. HST is equal to R into KT upon KT minus 1 into T3 into 1 minus P2 by P1 to the power KT minus 1 upon KT. For ideal gas, again we can write CPT, T stands for turbine, CPT minus CVT is equal to R. So CPT upon CVT is equal to KT. So 1 minus 1 upon KT is equal to R upon CPT. So CPT is equal to R into KT in divided by KT minus 1. So we can replace, simplify this. HST is equal to CPT T1 into 1 minus P2 by P1 to the power KT minus 1 upon KT. So this is expression for isentropic enthalpy drop. Now actual enthalpy drop, the process 3 and 4, we can write HAT, T for turbine, CPT into T3 minus T4. So turbine isentropic efficiency is equal to EST is equal to CPT into T3 minus T4 divided by CPT into T3 1 minus P2 by P1 to the power KT minus 1 upon KT. So CPT cancel out, we can write EST is equal to T3 minus T4 divided by T3 into 1 minus P2 by P1 to the power KT minus 1 upon KT. But again, T4S upon T3 is equal to P2 by P1 to the power KT minus 1 upon KT. So we can replace this. We can write EST is equal to T3 minus T4 divided by KT, T3 into 1 minus T4S upon T3. So on simplification, we can get EST is equal to T3 minus T4 divided by T3 minus T4S. This is expression for isentropic efficiency of turbine. Now overall efficiency of gas turbine cycle system, we can write overall efficiency is equal to network output divided by heat addition. So turbine power minus compressor power, or power we can replace head, power head, turbine head minus compressor head divided by addition. So we can write per unit mass, power per unit, or what is called work done per unit mass is head. So if both are in same, this should be in same unit. So we can write EST is equal to CPT into T3 minus T4 minus CPC into T2 minus T1. This is net work done per unit mass. divide by CP3 minus 2, sorry, CP32, that is process CP23 into T3 minus T1. So this is expression for overall efficiency of gas turbine system. Now same analysis has to be considered considering the gas is real. So because in real in industries real gas application is used. So again compressor is open system, so work done by the compressor on the system per unit mass is work head, which is expressed as the process 1 to S. So we can write HSC is equal to Z1 or Kc upon Kc minus 1, okay, close T1 into 1 minus P2 by P1 to the power Kc minus 1 upon Kc. Again, this will give negative value. To convert positive, this can be arranged as HSC is equal to Z1 into R into Kc upon Kc minus 1 into T1 into P2 by P1 to the power Kc minus 1 upon Kc minus 1. For real gas, a specific heat capacity for compressor is written C stands for compressor, C is equal to CPC by CV. However, in this case, we need to separately calculate CPC and CVC and then calculate Kc. But you cannot use this formula CPC minus CVC is R, because this will not give the good result, and that is why it is not advisable to use for real gas application. Now for the compressor, enthalpy rise is CPC T2 minus T1. So overall compressor isentropic efficiency is written as ESC is equal to Z1 or Kc upon Kc minus 1 into T1 break into P2 by P1 to the power Kc minus 1 upon Kc minus 1 bracket close upon CPC into T2 minus T1. So this is expression for compressor efficiency, isentropic efficiency in case of real gas consideration. For turbine, same way we can calculate. Turbine is also open system, so process 3 and 4 is isentropic process, that is work head. So HST is equal to Z1 R KT upon KT minus 1 T3 into 1 minus P2 by P1 to the power KT minus 1 upon KT. So work head is isentropic enthalpy drop. So isentropic enthalpy drop is written HST is equal to Z1 R KT upon KT minus 1 into T3 into 1 minus P2 by P1 to the power KT minus 1 upon KT. For real gas, again we can write the specific heat capacity ratio for turbine is written KT CPT upon CVT. Again we need to separately calculate CPT and CVT and then divide, but we cannot use this equation CPT minus CVT is equal to R, because this will not give good result. For turbine enthalpy drop, actual process is 3/4, so we can write HAT is equal to CPT into T3 minus T4. So turbine isentropic efficiency EST is equal to CPT T3 minus T4. This is for actual enthalpy drop divided by isentropic enthalpy drop, that is Z1 R KT upon KT minus 1 into T3 into 1 minus P2 by P1 to the power KT minus 1 upon KT. So this is expression for isentropic efficiency of turbine for real gas application. Now, how to improve the efficiency of gas turbine system? So one process called reheat cycle. So you see in the diagram, TS diagram, the after expansion in turbine, partial expansion from process P2 to P2 dash, again it is heated externally and then further expansion is done in the next stage. So this is one way through which efficiency of what is called gas turbine system is improved, that is called reheat cycle. And regeneration, you can see the heating of compressor outlet gas, this is outlet gas by the exhaust of turbine, because exhaust temperature is more than outlet. So this is called regeneration process, and through which also we can increase the efficiency of gas turbine system. Another is intercooling of compressor, because compressor requires intercooling to improve the efficiency of compressor. So after compression from process 1 to 2 days, again it is cooled in the heat exchanger and then further cooling, or sorry, further compression process takes place. So process 1 to 2 days is one compressor, then intercooling and then further compression. So intercooling, interstage cooling also helps in the efficiency improvement of gas turbine system. So I'm sure that you like this video and enjoy this. Thank you for watching.